Hey everybody, welcome to HPC Tech Shorts, and this is the where every week we take you to the HPC water cooler here in HPC Engineering at AWS, and talk to interesting people who are making the cloud a better place for all sorts of things related to our community. Last time we spoke about containers, we had Christian Kniep joining us from Germany and talking about sort of some of the HPC, the container 101 aspects of how containers work inside HPC. And we spoke about things, we sort of built up a body of knowledge there around how containers are working and what some of the central challenges are that they have in HPC. We finished up by talking about, hang on, let me just get the graphic up on the screen. We finished up by talking about how, containers now got the ability, evolved over time to expose, specialized hardware, things like GPUs and in fact, specialized networks, so that there's no loss of performance and there's a, complete fidelity of being able to control aspects of those things. This is the stuff that's really behind, some very large workloads that we do with, we support for customers who are running model training workloads on AWS Batch, using containers, using GPUs, and running at an extraordinarily large scale as well. So that's sort of run rate day-to-day activity for us, supporting customers doing that. So none of this is magic. None of this is novel and crazy and hardcore. It's pretty mainstream stuff. Anyway, I'm pleased to say that I'm joined by Christian again. Hey, welcome back to the show, Christian.
Hey, Booth. Thanks for having me again.
And today we want to knock off. We've got a challenge of knocking off a couple of big topics today. We want to talk about some container runtimes and how they react to how those have all grown up in reaction to some of the other challenges that HPC have got. And of course, HPC's got some big challenges around shared storage and wanting to make sure that we access shared storage, things like Lustre file systems really fast and not, don't lack any performance or fidelity. And then of course, multi-node parallelism, that's kind of what our community is all about at depending on who you ask. So let's get into that. Let's have that discussion. Where do we want to start?
Can you jump to the Maro, the whiteboard?
Yep. Let me just click on that button. I'm slowly getting used to this thing. So that's where we left off last time was with the GPUs.
Exactly. And yeah.
Today we're zooming in here, right?
Yeah. So as you said, we talked about CPU and GPU use and how to use special devices and how this works quite nicely for bioinformatics and other workloads where you need scale. But today we would like to talk about the more advanced HPC specific topics like shared file systems and then eventually Mpi and Slurm. And let's start off with the shared file system problem in quotes, because that's, I think, one that is pretty dominant and pretty sticky when people talk about HPC and containers. So as we saw last time, you can define very much how the container will start a process within the container. So you can say what namespace to use. You can also define what user ID and group ID to use. And this is the dangerous and very and the delicate problem that we can face with when we use Docker. So can you go down to this Docker run Alpine diagram? That's just the process flow. If you start a container using Docker, this is how it will actually interact, right? The Docker client in the user context will reach out to Dockerd.
Yep.
Dockerd will reach out to containerd to instruct him to download a container image and then instantiate the container eventually. Containerd will start a shim, like a containerd process that will just work or deal with standard out, standard in, standard error, and some more advanced monitoring and handling of the container, actually the container process, very lightweight. And the container dshim will start the container using runc, but that's beside the point. It will start the actual container process. So you can see it's very complex and a lot of layers involved. And if you start a container that wants to access a file system on the host, you can mount in the home directory, for instance. But when you mount in the home directory and you are able to control the user ID and group ID of the container, of course, you can mess with the home directory.
Yeah. Because
this is what I would like to show you in my screen. Can we switch to that?
Yeah, we can. Hang on. Let me add that. There we go.
So I'm a EC2 user here. I have a user, it's called Bob. His home directory is empty. And I will just put in a command that actually maps in the home directory from the host. It will use the user ID of Bob and the group ID of Bob for the process that is instantiated within the container. And the container process is a touch that writes to home Bob my file, right? So it's, and this is a totally works as designed example of how containers are designed here, right? So I wrote a file, and the file was written by a process that was owned by Bob, and the group ID was also Bob. So that's the expected result, and that's perfectly within the limits of container runtime spec here, right? So I created a container. But of course, this is super scary for people who have a shared file system they care about. And this is, of course, something that you cannot allow on an HPC system where you have POSIX file systems you need to deal
lots of users who could all do horrible things to each other if they felt like it. Yeah.
And if we go back to the picture, this is of course explained by this complex layered cake of API calls to root services, privileged services within the Docker ecosystem. If you scroll down a little bit to the next picture, just another way of looking at it.
Mm-hmm.
You have like the Docker engine in the middle. You have orchestration like Swarm or Kubernetes, also ECS, EKS. It's all like the orchestrators that can run and drive containers. Mm-hmm. But the containers you create are not meant to be issued or created in a shared system, like shared file system or with a multi-user file system with different users, because it's not designed for that. As we can see, as we saw last time, you can pretty much command the container to be constrained or less constrained. And if we look at the right-hand side, what scheduling means for HPC, you have like your HPC workload scheduler. Maybe it's using Slurm. So you have a Slurm daemon that instantiates processes similar to what the Docker engine does, even though it's not containerized, but it instantiates processes on behalf of the user. But the difference, of course, is that Slurm will only instantiate a container or a process, for the user ID that asks for it, right? So Bob can only run processes under his own user ID. He cannot just say, I'm Bob, but I want to run under Alice. Slurm will make sure that this is never going to happen. And this is the big difference between those two. And since Docker or the Docker ecosystem, the traditional containers, they are a whole cake of different layers of container technology, right? They are runtime, so they instantiate a container. They are also a scheduler. They are also a lot of different things. And for HPC, we don't need all this layers. We just actually need the underlying runtime layer. So that's what we want, right? We want to instantiate, and on the right-hand side, we can see this here. We have job process 1, a non-containerized native service. On the right-hand side, job process 2. If we can just containerize this process, that would be awesome. And this is where HPC runtimes fit in. We have like the early runtime, Singularity, Charlie Cloud, and Shifter, which were soon after Docker was released, were developed on various national labs in the US. They are all just trying to apply container technology to this one problem of spawning a process. And over the years, more runtimes came up. I think it's almost like JavaScript libraries at some time where like every other day there's a new runtime. But essentially, they're all doing the same thing. And this is, I think, something that I would like to make sure that everyone understands as well. HPC runtimes are not very different anymore. They are doing the same thing. They are instantiating a process with more or less limits on how the process can interact with the system. And one of the HPC runtimes that I like the most because it's very much based on OCI standards, and it's very, very transparent, very slick, is Saros. So the difference to the picture we saw above is that we are always in the user context. So there's no way I can create a container as Alice who is going to interfere with Bob, because the process of creating a container is Saros uses runc to instantiate the container, and then the process will just run, right? And I can show this in my screen again.
Yeah, just click
by
get your screen up. There we go.
So if I do this here, I will run a Saros container touching a file in my own home directory. Right, and we can see my file. This file is, of course, owned by myself because the container was run under my user ID. And to illustrate this even better, I can just show my ID here. If I do the same in the container, we will see that it's the exact same user ID here, right? So it's just that this container is not going to break out of my user context. And this is the beauty of HPC runtimes here, or runtimes in general. They are just creating a container on behalf of the user, but not with a layered cake of API calls, just a straight process that is forked or executed.
That makes sense.
Okay, so let's move further down a little bit. Can we?
Yeah.
And this solves this intermediate problem that I showed here as intermediate problem with shared file systems, right? Because, and for sysadmins out there, you can think of this HPC runtime as the normal way of executing a process. There's it's no difference to you if the process is containerized or not, because it's just a process that is more or less forked with the same principles as a normal process. So a user using a container runtime cannot break out of it. I mean, of course, there are edge cases.
But that makes sense so far. So how do we? So how do we? Well, okay, keep talking, because I think you've got.
Yeah, and this is used by the biggest supercomputers in the world, right? Saros comes from CSCS, so they are running this on their couple of 5,000 node system. So it's not like something that someone uses in his little prototypish environment, right? It's serious stuff here. So that should put away the concerns about shared file systems, and I think that's one of the most prominent ones that we need to demystify.
And you've run workshops. I mean, we'll put some links to these workshops in the show notes. You've run workshops that have shown people how to actually run Saros inside AWS parallel clusters. So they've got literally that environment you were talking about, which is a standard a canonical Beowulf cluster running on a bunch of instances in the cloud, with Slurm as the scheduler, with Saros as the runtime, with fully containerized applications, Chromax, etc. Running in that environment, right?
Exactly, yeah, and even more so, I try to incorporate in this workshop. I try to incorporate all the major runtimes there are, right? So Singularity, Charlie Cloud, and Saros and others, so that people can experience different runtimes and realize that it's more like a Vim versus Emacs discussion in some sense, because it's and there's a link in the description.
There's a link down there. Yep.
But I think it's very important that we all come to the conclusion that HPC runtimes are not super different anymore. They are a couple of them more progressive, and a couple of them with a longer history. They need to stick maybe with their API, and they are not progressing that fast. But essentially, they all do the same thing. And this is, I think, what people should really incorporate.
If anybody out there is particularly attracted to a runtime and they think that Christian has done them any disservice, they can find him on Twitter and have an argument.
I stopped having. I'm happy to have little scribbles.
I'm just attracting the trolls. It's okay. I'm just attracting people.
But I stopped caring about which particular runtime like 2 years ago. So I have my favorite, but I'm not condemning others. Okay, so let's talk then about Mpi and Slurm. And can we switch back to my screen?
Certainly can. Here we go. Kniep, there you go.
So now we are going to use Slurm as a scheduler, and we are just using a couple of batch scripts to submit jobs here. The first one is just executing or compiling a hello world using Intel MPI natively, right? So I will just create, or it's already created, but I can also like submit the job just for the fun of it. Let me copy it. Here we go. Here we go. So I will submit it to my C5N queue. That's the queue that holds a couple of C5N 18XL instances. This should run rather quickly. So let me.
If it doesn't, then something's horribly wrong.
Yeah, that's true. It's job 40. Here we go. Compiled the hello world, and off we go. The next one I will run is a native MPI run. Pretty unimpressive, I think. We will just run the just compiled hello world example using Slurm.
And okay.
So that should be also pretty fast. Here we go. We're running on 2 nodes. We can see the ranks. Nice. Okay, and let's focus on this here for a sec. Like MPI run binary, right? This is the usual way we use MPI, and in Slurm it also takes care of all the magic of instantiating the MPI domain and all this nitty-gritty details. So we just need to run this. And if we now use Slurm for the Ceros for this, we will just submit the same command, but hello Ceros. We will have Ceros run MPI and our container image just introduced into the MPI run command. And this is similar to in other HPC runtimes. It will look pretty much the same.
And just walk me through the details in that command there. You've got a path name there which has got Debian in it. What's the key thing there?
Yeah, this image is the Debian Buster image with mpitch installed. So
and are you running on an actual Debian cluster here right now, or are you running?
No, this is of course Amazon Linux 2. And as we discussed before, like containers, that's the new part about it. Containers are just abstracting away the underlying OS. We are just interacting with the kernel for like usual stuff. Then if we use EFA, of course, we will use the driver. If we use GPUs, we will also use the driver within the container. But essentially, we are encapsulating this in the container.
And that's actually really cool. This is if this is not banging in everybody's eyeballs enough, this has made this completely portable. Portable between distros. We've isolated ourselves from being too dependent on the nitty gritty details of a distro.
And of course, for HPC users, this looks a little bit oversimplifying here because MPI, of course, has its variants, has API compatibility. So, as I said, I'm using Intel MPI because Intel MPI is installed on the host, and I know that that's the one that I want to use here. But within the container, I have an mpitch variant just installed, like proper mpitch installed in the container. And what Ceros does, similar to what we discussed last time with GPUs, it will look for the MPI on the host. It will figure out, okay, I know the sysadmin configured that Intel MPI is the one that I want to use on this host, and it will map the correct libraries into the container on the correct in the correct location, and make sure that the hello world that I compiled will actually work with all the speedy interconnects that I have on my host. So it's a host dependency that is configured by the system admin, and I can show you the configuration here real quick. It looks something like this. It just defines what the MPI library is that I want to introduce into the container. It defines what my bind mount is for this. So it's EFA. It has this device here, and all the dependency libs that I want to introduce into the container. And this is pretty neat, and I cannot be more amazed by this because it's super easy. You just define, as a sysadmin, you define what is the MPI that I want to use for this, and you need to instruct your users to just have a flat or a normal mpitch installed and compile against this, because you can swap out the underlying interface and drivers within the container. So that's pretty neat. And this is per node. So if I'm going with this, I'm going to an instance that maybe has no EFA, but only ENA, then I can just use different libraries and don't bind mount the device for EFA to make sure that it runs on a non-EFA system. And it's abstracted away from the user. And I think this is very important to take away here.
Okay, so that is really neat.
I think we didn't show the output yet, did we? 42. Here we go. It looks like exactly what we did.
All your CPU cores belong to us. It's good.
So
yeah, perfect.
It's the same output because it's actually running similar.
Okay, so that's actually particularly cool. The fact that you can abstract, it's another layer of abstraction that could actually prevent a lot of folks from accidentally tickling. I don't know. They may accidentally pick the wrong MPI for a system, and I know that we've got a show coming on this in a few weeks' time where we're just going to talk about just some simple debugging procedures to make sure that when you're running stuff on EFA. Using say OpenMPI or MVAPITch or Intel MPI, and you're running on EFA on AWS, how to make sure that you don't accidentally invoke your MPI run in the wrong way and end up pushing all of your data out over TCP packets instead of over EFA, right? Because that they lead to very different outcomes in terms of application performance, and this would be a really neat way of actually avoiding those kinds of pain points, right?
Yep. Exactly, and I think what helps me understand this, or helped me in the early days to understand this, is that it's super neat that you can pretty much separate the concerns of host-specific configuration, like I have EFA with Intel MPI, and the application itself, because I think this is what people struggle when they design or develop or use HPC applications. It's always like you need to be very much aware of what system you are running on, or you need to have a good relationship with your sysops guys so that they make sure that your system or your application runs neatly. And with this approach, you make this very separate. The sysops guys configure the hooks, they configure GPU and EFA and MPI setup, and the application is just
so the system takes care of the system. The application person takes care of the application. You tightly package all of the app and all of the libraries that it's dependent on into a container, and you've got a really nice, neat handoff between each of the people involved in the chain.
Yeah.
Right? Okay, that's particularly cool. What do we want to say about OCI hooks and so forth? Because we're getting close to time again, but I know that we do have that on our shopping list of things to talk about. Maybe we have to
so what we saw, what I showed in this YAML file that I showed is a definition of an OCI hook. So it defines within the life cycle of a container, you can have different hooks. One that is just started before the container process starts with, this is what we use here to introduce libraries and maybe bind mount something that we want to have in the container. After that, the process starts, and you can have hooks that are started after, or that are fired when the container exits, or maybe in between. So you can have different lifecycle hooks, which is pretty neat to interact with the container automatically. And also, again, depending on the host, right? You can configure this on the host, and the user does not need to know about it, and it's transparent to the user. So it's pretty cool. And I think we should talk about this at some point, but I guess we will quickly run out of time, and we are already on 20 minutes mark.
Yeah, but that's okay. That's all right. It gives us another reason to come back and dive into this a bit more. I'd like to actually come back and do that. So if you're okay, we'll come back in maybe in a couple of weeks, and we'll get into OCI containers and all of the stuff associated with that, and do a bit of a deep dive in there.
Yeah, I think you know me already enough that you talk about containers, and let me talk about containers publicly. I'm always in.
That's awesome. Well, thanks for coming today. For everybody who's watching from home, if there's if there's stuff that Christian said that you want to pick up a conversation with him, he's available on Twitter. There's his Twitter handle. Pick up a conversation with him on Twitter. Containers are a big space, and there's still a lot of work to be done to make the cloud and a perfect place for HPC containers. So we're all still working in that space. Nothing is ever finished, and so we'll just keep going. So help guide us on that journey by in particular by giving us some feedback on what your use cases look like. What does work, what doesn't work, what you're struggling with. Anything that we can do to remove the undifferentiated heavy lifting, which is to say making things easier for you, we want to try and do. So with that, I guess I'll finish up today by also saying that if you've got thoughts and ideas for future tech shorts, topics that you want to see us talk about, areas that you want to see us dive deep into, please find us on Twitter. Our DMs are open. If you like what you saw today, please click the like button, of course. If you really like it, subscribe to the channel, share it with your friends and your colleagues, and let them know what we're talking about over here. We'd love to be engaged. Christian, thank you. Thanks for coming today, and I guess we'll have to work on the calendar and see where we can fit the next one in.
Alrighty. Thanks, Booth.
Thanks, everybody.